Okay, I want to talk about the coupon collector problem. Now we've seen this in disguise in lecture 2, where we had all these examples with boxes and marbles and how you pick the different color marbles and so on. And so the same problem came up with two different, seemingly different descriptions, but it actually was the same exact problem. The coupon collector problem, which has these one-step transition probabilities for the underlying chain. And so you can find it in Ross, and you can review that lecture as well to kind of see all the connections. But the idea of this coupon collector problem is that there are these n distinct coupon types, and so you're trying to collect all n distinct coupons, but every single time you get a coupon, they're kind of all equally likely to find their way to you, right? And so when you start with 0 coupons, you obviously get the first one, and it's distinct, right, in one step. So probability from 0 to 1 is always 1. But then once you have this one coupon, then in the next shot, maybe you'll see the same coupon again, and so you don't really move up in the pecking order, right? You've seen the same coupon. Unfortunately, it's a small probability, 1 over n, right? It's of seeing the same coupon again, right? With the much higher probability, 1 minus 1 over n, you move forward, and now you have got these 2 coupons, and then so on and so forth, all the way up until the state n minus 1, where I guess you're gonna have to spend a lot of time waiting for that one your final coupon to kind of fill your collection, right? So this probability going from here to here is 1 over n. For n large, that's pretty small, right? So you're trying to get this last coupon, and you kind of have to just wait forever, and then finally you get it, and here the happy coupon collector is there. So what's the state? Why am I bringing up this example? It's mostly to show you that that sometimes you have to do very little math with these things. So here you can kind of get the answer by intuition, and I would recommend always using intuition in the setting of these stationary distribution calculations. It just saves you a lot of work. So here, and what happens eventually once you let time run for a long enough period, right? Eventually the story is going to end well, and the coupon collector is going to get all the end coupons, and that's going to always happen, right? There's going to be this positive probability. It's a finite state chain, so eventually you're going to after a long amount of time, depending on how lucky this collector is, they're going to get to this final state n, and then they're going to stay there, right? And so if we think of pi x as the probability of the chain being in state x after a long time, well, we're certainly not going to stay at 0, we're not going to stay at 1, we're not going to stay at 2, right? Those are, after a long enough time, those are all going to 0, right? You have to be, something really bad has to happen to stay at 2 coupons, right? You're just always going to keep accumulating them. And so the answer is, for that reason, this, right, pi n is equal to 1 is the stationary distribution, and what that means, that pi x is equal to 0 for all x strictly less than n, right, or not equal to n. And so we didn't have to do much. You can try to verify local balance and global balance. So like global balance, you would start with pi n and ask what states lead you to n. Well, it's n minus 1 and n. So we can write pi n times the probability of getting into pi n, which is 1, plus pi n minus 1 times the probability of getting to n, which is 1 over n. However, this is set to 0 because of that, right? And so this goes away, and you have verified that pi n equals pi n, so therefore global balance holds. Weirdly enough, you should be able to do this with the local balance condition also, but there are some caveats that we'll come back to when we look at reversible processes and the concept of reversibility, of kind of looking at this as a movie forward in time and backward in time. We'll see whether this chain is reversible or not, and what that means. But local, you should be able to verify local balance here as well, even though there's some kind of weirdness about that. So yeah, so that's a simple one, right? And hopefully you're kind of using your intuition about the behavior of the chain to to supplement all the math calculations you have to run through with global balance or local balance and so on.